Hello dear students of +1 medical and non-medical respected teachers. Today I am going to discuss second part of the chapter rotational motion. The second part I am going to discuss what is torque and expression for torque acting upon a single particle and torque acting upon a rigid body. So first, what is torque? It is defined as the moment of force or turning effect of force. Torque is equal to moment of force or turning effect of force, and it is equal to the product of the magnitude of force and perpendicular distance of the line of action of force from the axis of rotation. So suppose P be a particle lying in xy plane having mass m, that OP is equal to r, or OP vector is equal to r vector, that F vector, the force acting upon the particle which produces torque on the particle. Then let theta is equal to angle between direction of r vector and f vector. Then produce line of action of force in the backward direction. Draw perpendicular ON from region O. Then ON is the perpendicular distance of the line of action of force from the axis of rotation. Because xy is the plane in which particle lies and z axis is the axis of rotation. So x, y and z axes are three mutually perpendicular axes, as we already know. Then torque will be equal to F into perpendicular distance, that is F into ON. Or from this right angle triangle ONP, ON upon OP is equal to sin theta, or ON is equal to R sin theta. So substitute the value of this ON in this equation. We have tau is equal to RF sin theta, which is the required expression for torque acting upon a single particle. In vector form, tau vector is equal to R cross F vector. It means torque is equal to the product of cross product of position vector and force vector, and direction is given by right hand thumb rule or right handed screw rule. So R cross F, so it will be along z axis. Special cases, when theta is equal to 0, sin 0 0, torque will be 0, that is minimum. So when force acts along the direction of position vector, then there will be no torque. Or even when theta is equal to 180 degree, then torque will be 0. That's why we cannot open or close the door by applying force parallel to the plane of the door. So if this is a door, we cannot open or close the door by applying force like this parallel to the plane of door. If this is a door, this is a door. When theta is 90 degree, sin 91, torque is equal to maximum RF. So maximum torque is produced when angle between R and F is theta is equal to 90 degree. So it is very easy to open or close the door by applying force at the 90 degree to the outer edge of the door, like this, because torque produces maximum. Third, when R is 0, torque is 0. It is difficult to open or close the door by applying force at the hinges of the door, because axis of rotation passes through the hinges of the door. So this question may be asked. Then to produce more torque, R should be as large as possible. For example, in case of hand pump, the handle of the hand pump is made long to produce maximum torque with small force. So, there are so many applications of this torque in daily life. Now, torque acting upon a rigid body. Suppose we have a rigid body. Rigid body means a body is said to be perfectly rigid if its shape doesn't change under the influence of external forces, or distance between any two particles of the body remains fixed under the influence of external forces or force. But there is no such body in this universe which is perfectly rigid. There are some bodies which are nearly rigid. Suppose rigid body having masses m1, m2 and so on, mn. Let r1, r2 and so on, rn be the normal distances, perpendicular distances of the masses from the axis of rotation respectively, which is xy. At F1, F2 and so on, F can be the external forces acting upon the masses M1, M2 and so on, Mn respectively. Then torque acting upon first particle of mass M1 is given by definition R1 F1 sin 90. Because it is a rigid body rotates. So mass M1 will cover a circular path. So sin 90 will be 0. Angle will be 90 degree or sin 90 is equal to 1. Therefore tau 1 is equal to R1 F1 or F1 can be written as M1 A1 or R1 M1 R1 alpha or tau 1 is equal to M1 R1 square alpha because A is equal to R alpha. So torque acting upon first particle of mass M1 is given by M1 R1 square alpha. Similarly, second particle tau 2 M2 R2 square alpha and so on. Nth particle tau n will equal to Mn Rn square alpha. Total torque will equal to tau 1 plus tau 2 and so on tau n, or tau is equal to M1 square plus M1 R1 square plus M2 R2 square plus so on Mn Rn square into alpha. Alpha is common, so tau is equal to I alpha, where I is equal to M1 R1 square plus M2 R2 square plus so on Mn Rn square is equal to summation Mr square. Is called moment of inertia of the rigid body. So tau is equal to I alpha is the required expression for torque acting upon a rigid body in terms of moment of inertia and angular acceleration. If alpha is equal to 1 unit, tau is equal to I. From this we can define torque or moment of inertia. It is moment of inertia is equal to the torque required to produce unit angular acceleration. Torque required to produce unit angular acceleration is called moment of inertia. This is the definition of moment of inertia. You can also note tau is equal to I alpha is the equation in rotatory motion, which is similar to F is equal to Mn linear or translatory motion. So instead of F we take tau, turning factor of force. Instead of A we take angular acceleration. Instead of M we take I, moment of inertia. So moment of inertia will play the same role in rotatory motion as mass does in translatory motion. This is all about torque acting upon single particle or rigid body and definition of moment of inertia in terms of torque and angular acceleration. So for next video, stay tuned, be happy, all the best.